Hello, I'm a professor of geophysics at SDSU. My research focuses on the physics of earthquakes, in particular earthquake rupture dynamics and how earthquake dynamics produce strong ground motion, crustal deformation, and tsunami. Most of the work involves computational mechanics. In the last 15 years also, my research group focused on subduction zone earthquakes and tsunami generation. And this work has been funded by NSF, and you can see some major grants here. And the first NSF grant I received was back in February 15, 2011. This was actually before the 2011 Tohoku Oki earthquake that occurred on March 11th, 2011. One motivation behind our work is to understand the physics of a special class of earthquakes called tsunami earthquakes. And this type of class of earthquakes was first identified by Dr. Hiro Kanamori back in 1972. So tsunami earthquakes have two anomalous characteristics. They generate very large tsunami compared to their surface wave magnitude. But at the same time, the seismic radiation is depleted in high frequency. Since 1972, in the last 5 decades or so, a lot of seismic data also indicate that tsunami earthquakes have other characteristics as well. So they tend to occur in the upper 15 kilometer. That's considered a frictional stable region, so where you don't expect to have any earthquakes. And tsunami earthquakes also tend to have slow rupture velocity and long rupture duration. They also tend to have low energy to moment ratio. That means they not only have depletion in high frequency radiated energy, but the overall radiated energy is low compared to the other earthquakes with same moment. Most earthquake models are based on elastic dislocation theory. So this type of models cannot explain the puzzles of tsunami earthquakes. So they couldn't explain why tsunami earthquakes have such anomalous characteristics. So in 2012 and 2013, with my former student Evan Hirakawa, we proposed inelastic deformation. So basically, if you have weak sediments in the overriding wedge, because the sediments have weak strength, so the material response will not be elastic anymore. So when you have inelastic deformation, you actually generate tsunami more efficiently with diminishing slip on the fault. Well, in the elastic model, you can see in order to generate a big tsunami, you need large shallow slip. But most the plate interface, near the trench is very shallow. So large shallow slip produce mostly horizontal motion. So the efficiency to generate vertical displacement is actually low. But this is not the case when you have inelastic deformation. So mechanically, inelastic deformation is a large energy sink. So it absorbs energy. And this leads to slow rupture velocity, deficiency in high frequency radiation, and a low energy to moment ratio that I showed you in the previous slide. The concept of inelastic off deformation is not new. It's widely used in the community to model strike slip earthquakes. So it was first introduced by Dr. Joe Andrews in 2005, and in 2D in 2008, and 2010, I worked with Dr. Joanne Juice to extend the inlet deformation model for the first time to 3D. And we were able to show that the co-seismic inlet deformation of the fault actually resemble a flower. So this is like a flower-like damage zone, because the yield criterion we use depends on the confining pressure. But the confining pressure within the earth is also likely depth dependent, because yielding occur more easily near the surface. So you can see this the widening of the damage zone near the surface. As I mentioned earlier, most earthquake models are elastic dislocation models, so they require large shallow slip in order to explain the tsunami generation. So here are three representative slip models of the 2011 magnitude 9.1 Tohoku Oki earthquake, using geodetic data, seismic data, and tsunami data. And you can see all these three models have large shallow slip near the trench, over maybe 50 meters along the trench. They require because they need large shallow slip to generate uplift. But these large shallow slip models cannot explain one key observations in the 2011 Tohoku earthquake and tsunami. That is, the largest tsunami run-up height, showing here, you can see, is actually more than 100 kilometers north of the 2011 epicenter. The large shallow slip updip from the epicenter actually was confirmed by the differential bathymetry before and after the earthquake, and you can see these 5 profiles here are are showing here more clearly, and the red numbers here showing you the large horizontal displacement. But one big question is, if you have large shallow slip updip from the epicenter, why did the largest tsunami occur more than 100 kilometers north? In 2017, there are 2 differential bathymetry profiles were published in the northern Japan Trench, and you can see here in these 2 northern profiles, and there is no large horizontal displacement. And you can see the red numbers are the amplitude of the horizontal displacement. So there's no large horizontal seafloor displacement that indicates there were not large shallow slip at the trench. So if there's no large shallow slip at the trench, what produced the large tsunami along this coast here? This coast is called Senryuku Coast. So this is the big puzzle about the 2011 Tohoku tsunami. In 2019, with another former student, Shiying Nie, we published a first 3D dynamic rupture model with wedge plasticity. This is again for a magnitude 8 earthquake, like a tsunami earthquake. So it's not for a magnitude 9 Tohoku Oki earthquake. But in this paper, we proposed a very important concept. That is, when you have along strike variations of material strength, for example, due to different thickness of sediments along the trench, and you can have inlet deformation when you have weak sediments, a lot of weak sediments. If you don't have a lot of weak sediments, then you will have you tend to have elastic wedge response. So this is what we introduced. So we introduced a variation of different closeness to failure parameter, and you can see here in the southern part where you have elastic wedge response, you tend to have large shallow slip, and you can see the seafloor displacement is more parallel to the fault. However, when you have weak material in the overriding wedge, and here, then the inlet deformation can actually generate uplift more efficiently without shallow slip, with diminishing shallow slip. The slip is shown by this magenta curve. And you can see without large shallow slip here, the inlet deformation generates more efficient seafloor uplift. And the seafloor uplift has narrower wavelengths compared to the uplift produced by the elastic deformation. So very clearly, larger and narrower inelastic uplift can be generated by inlet deformation. And this can explain the 2011 Tohoku Oki earthquake and tsunami. Finally, in 2023 and 2025, with another former PhD student, Yue Du, we published our inlet deformation model for the 2011 Tohoku Oki earthquake. And we show that the inlet deformation can explain the puzzling, tsunami observation. Why the largest run-up occurred more than 100 kilometers north of the hypocenter. And in 2023, November 15, on this date, I gave a seminar at USGS, and you can see here is the link, and you can hear the whole story about our work. Because in the community, most people think the 2011 Tohoku tsunami was produced by large shallow slip, and we simply think this is a misunderstanding. This is a misinterpretation. On the picture here, you can see this was in Noda, Iwate Prefecture, Japan. I was in front of a tsunami monument. The run-up height here near this site was over 38 meters. I think it's the second or third largest run-up ever observed in the 2011 tsunami. And behind me here, you can see the Pacific Ocean, and this is the northern part of the Senriku coast. I did not have a smiley face because I was concerned that the scientific community may misinterpret the physics of the 2011 Tohoku tsunami. So if you're interested, take a look at this seminar. Also, if these topics are interesting to you and you would like to pursue a PhD doing this type of research, please free to contact me. Thank you.